Good day. For those of you who do not know us, we are the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to introduce dynamic memory allocation. So, in this lesson, we will revisit static memory allocation, that is, local variables and parameters, introduce dynamic memory allocation, and introduce the new and delete operators. Now, just a comment on the last lecture. In this course, you will never need to know a specific address of any variable or any memory location. In this course, we will simply call functions or operators that return addresses. Those addresses will then be allocated or assigned to pointers, and then we will access and manipulate what is at that address using those pointers. Thus, you never need to worry about what a specific address is or its significance. In fact, the only time you will ever be looking at addresses is if you are debugging your code. Even then, you don't actually care about the exact values. Instead, you will simply be comparing addresses against each other. That's it. Are these two addresses the same or not? That's the same as telling, are 57 and 582 the same number or not? All right. Up until this point, all memory has been in the form of either parameters or local variables, as well as, of course, instructions themselves, but that's an aside. The compiler arranges for the memory to be allocated when the program is executing. And as we've already discussed, the memory for local variables and parameters is allocated on the call stack. When a function exits, the only data that remains are any values that are returned from that function. Now, such memory allocation is called static. This is because the arrangements for allocating any such memory are made by the compiler, and you cannot change how that memory is allocated while any program is executing. Now, suppose that when we start executing a function, we don't know how much memory is required. For example, we may be writing a program that is a text editor, and the user could be using that program to type a 10-word response to an email, or a 1,000-line program, or perhaps even a novel. As the user types more and more characters into the letter they are writing, how do we keep allocating additional memory? After all arrays, as far as we know right now, are fixed in capacity once they are declared. And yet, the user can always keep on typing no matter how much they've already or previously written. There are solutions with statically allocated memory, but they're very awkward to use. So suppose you were trying to write a program that implemented a text editor. Is this a reasonable approach? Let's just allocate a character array of size 1,000,000, and we'll assume that the first character is a null character, meaning that at this point the string is empty. Then as the user continues to type text into this letter they are writing, we will modify this array. Now, using a single array with 1,000,000 characters is a horrible way of storing a text file. First of all, an email response seldom requires more than, say, 1,000 characters, so that's a lot of wasted memory. And even if you're J.R.R. Tolkien finishing off The Hobbit, you actually only require about half this memory. Of course, that does fit into our array, but The Lord of the Rings does not. So suppose Tolkien is using our text editor to finish The Lord of the Rings, And there you go. Except there's a problem. Having finished everything, he discovers a typo. Well, to change Uzi to Uzi requires that every character after the Z, after the O, actually, has to be moved one character to the right. That's a really large for loop to make one small change. Suppose you had a similarly sized document and you wanted to suddenly make a search and replace of all British spellings with their corresponding American spellings. Well, that's okay because the American spellings tend to be a little bit shorter. But what happens if you're going the other way around? You might be just under 1 megabyte, but with the British spellings, that might actually push you over that 1 megabyte limit. We essentially need some way of saying, hey, we need some more memory right now, but we have to determine how much memory is required at runtime. And on top of that, we have to be able to change how much memory is required once again at runtime. Question, where can we get this memory? The memory that required for a function call is always placed on top of the memory required for the previous function call. So we can't really use the call stack. And so what happens if we do need 3 bits, 1 byte, 37 bits, 42 bytes, or we need 2.4 megabytes, which is what we require to store The Lord of the Rings? Now, memory management is an issue dealt with and within the purview of the operating system. When you execute a program, it is the operating system that allocates the memory for the call stack and also the memory for the instructions. It is the compiler that determines how to use that memory for the allocation of local variables and parameters, but it is the operating system that initially allocated that memory. Thus, if you want more memory, you must make a request to the operating system. Now, question, how do we allow this transaction? Well, basically, we are going to ask the operating system for an integral number of bytes. The operating system will then try to find sufficient memory to satisfy such a request. Let's see where that memory may be. All right, let's suppose you need a little bit of memory, 4 bytes. Now, some memory is going to be allocated specifically for the program instructions and any literals. And we've already discussed this. This will be closer to the start of memory. At the end of memory is the memory allocated for the call stack, and the compiler is going to determine how this is going to be used. Now, you may be wondering, how is this possible if you have many different programs running? This is actually done through something called virtual memory, where the operating system can arrange it so that every single program seems as if it is using all of memory for itself and itself alone. But that's later on in your undergraduate career. All other memory is used for dynamically allocated memory. That is, memory that the operating system can give out as needed based on requests made by various programs. This memory is known as the heap. So, suppose that you ask for 4 bytes of memory. The operating system is going to look through all of memory and determine if there's any 4 bytes available somewhere that can be allocated to the program in question. Now, not only is your program requesting memory, but all other programs that are currently running require memory, and so some memory may be allocated to other programs, some memory may be allocated to other requests that your program has made. However, here we've found a block of memory that is currently unallocated. The operating system will then flag 4 bytes as being given to your program. Those 4 bytes now belong to you, and the operating system isn't going to touch them. There's still 11 bytes left over, at least in this contiguous block of available memory, and the operating system will keep track of it, and it may allocate that to some other request. Now, how are you going to access this memory? Basically, how does the operating system tell you that these 4 bytes of memory are now yours to use? Well, the common solution is to simply return the address. The 4 bytes you've requested are at memory location 9BC 0A9 3258. Fortunately, you don't actually have to know that. So, the operating system is going to return this address, and we are simply going to assign this address to a pointer. Easy enough. Now, one question though, however. Let's say you need memory. How are you going to calculate it? Fortunately, the compiler is doing the work for you. If you need sufficient memory to allocate a double, then the compiler will figure out that a double is 8 bytes. If you need an array of 50 integers, the compiler will determine that you require 50 times 4 or 200 bytes. So the compiler does the work for you. You simply have to indicate what memory is required. The keyword new defines a unary operator in C++. Being a unary operator, it only takes one operand, but that operand is going to be a type. In addition to the type, it may also take an initial value, although as we've seen in this class, you should always initialize everything where possible. Now, when this call is made, it will request sufficient memory for the type in question to the operating system. It returns the address supplied by the operating system. All right, let's see this in action. So let's see what happens here. First, we've declared p_int to be a local variable. It's a local variable. The memory for its 8 bytes is allocated on the stack, and it is initialized with the default value of an address. That is all zeros. Now we call new. The compiler knows that an int is 4 bytes, so behind the scenes, a system call is made requesting 4 bytes. Now, the operating system finds 4 bytes and flags it as being allocated to your program. The operating system then returns the first address of those 4 bytes. The new operator now carries on and initializes that memory with the value 42, of course in binary. Now it may either be this or something else depending on whether or not it's little endian or big endian, but don't worry about it. Here we see that these 4 bytes have been initialized with the value 42. The value of that address is now returned by the new operator, and it is assigned to the local variable p_int. When we now print this variable, that address is printed to the console. Now, here the program finally exits, and the operating system realizes that this program still has some memory allocated to it, so it flags it as being unallocated. The memory still contains the value 42, but that memory is now available for another program to use. Now, note that we can even use the new statement inside the initialization of the p_int variable's declaration. All right, Next, we're going to use this memory. The compiler has given it to us. Let's do something with it. All right, up until this line, we've already printed out the address stored in p_int. So when we execute this line, placing the star in front of the pointer variable, we will actually print what is at that memory location. And at that memory location is the value 42. So 42 will be printed to the screen. Next, we assign to that memory location the value 91, and that changes the memory below. So now we see that in that memory location, the value 91 is stored, and 1011011 is the binary representation of 91. With the next line, we now print what is at that address. And of course, what is at that address now is the value 91. Okay, so at this point, the program returns, it's finished, and the memory allocated is reclaimed by the operating system. Note that the operating system does clean up your mess after the program exits. That is, it deallocates any memory that was allocated. Is this actually a good idea? Suppose that you are running your web browser and you have an open tab. That tab probably requires a lot of memory to be allocated. For example, every single image here that you see needs to be allocated for this tab. On top of that, if you were to now close that tab, should that memory still be allocated to the browser? Should that memory still be sitting somewhere in the operating system's heap, flagged as being allocated to this particular browser? What happens if another browser or another program needs that memory? We need some way of giving the memory back to the operating system, or saying, hey, that memory you gave me, I don't need it anymore, but thanks. So just like programs can request memory, programs can also explicitly tell the operating system when that memory is no longer necessary. Here is the statement in question. The delete operator is a unary operator that takes a pointer as an operand. So basically, all this does is take that address stored in p_int and send it to the operating system. It is the operating system that says, okay, you are telling me that the memory at this address is no longer required. The operating system can then deallocate that memory and flag it as being deallocated so that it can use it again somewhere else. Now, something that's very, very important, and a lot of students somehow seem to think there's something more magical happening. No, that's all that happens. That address is sent to the operating system, and the operating system simply flags that memory as now being available for someone else. So p_int still has that address assigned to it. So the next thing we're going to do is we want to forget that address. So what we do is we set p_int to the 0 address. And the 0 address is stored in a keyword null pointer, which is essentially, in this case, a 64-bit 0. It's important to remember that the delete operator simply sends the address to the operating system. I'm reiterating this so that you hopefully understand. And remember this, it doesn't do anything magical. It doesn't It literally does nothing other than send that address to the operating system. It's the operating system then which flags that memory as no longer being allocated to your program. The problem is, through that variable, however, you still have access to that address. This could potentially be a problem. So let's see what's happening here. With this statement, we print out p_int. Now, we may re-execute this program, so we may get a different address, because each time we run the program, the operating system could give us a completely different block of memory. All right, now when we call delete on p_int, we simply send that address to the operating system. Right now, p_int is still assigned that address, and when we print it out, we get that exact same value. What we need to do is we have to now forget that address. How do we forget what is stored in a local variable? We overwrite it with a new value, and that new value we're going to use is the keyword null pointer, which is essentially a 0 pointer. So now the local variable p_int is assigned 0. So now when we print out that address, we see 0 printed to the screen. We have told the operating system we no longer need that memory, and we have now assigned 0 to that local variable. Now, there are many different issues with pointers and dynamic memory allocation. This can cause concern for a number of students. So over the next few lectures, we're going to address a few of these issues, and hopefully these lectures will give you the confidence necessary to understand this fundamental aspect of programming, the ability to dynamically allocate and deallocate memory. Following this topic, you now understand some of the limitations of local variables. For example, the size of arrays is fixed, and the memory for local variables, be it local variables or local arrays, their scope is limited to the function itself. You now know that memory can be allocated at runtime, and this is known as dynamic memory allocation. You are familiar with the new and delete operators for allocating such memory. Here's the references, the colophon, and a disclaimer. Cheers!